Okay, so 3 minutes. What is it? It's gravitational time delay in this room. Let me tell you what is it I want to estimate. I have a watch, measures time. I have a phone, also measures time. I can throw up the phone and then catch it. So this is 2 events. This is my watch. 1. This is my phone. 2. There's tau 1 and tau 2. The objective is estimate delta tau over tau defined as tau 2 minus tau 1 over tau 1. Let's not worry about the sign. This is what I want to estimate. What are the dependencies? What can it depend on? Well, it can depend on the height. Let's say that was 1 meter. It depends on the acceleration, 9.8 meters per second squared. It can depend on c. It should depend on c. It's a relativistic effect. It's also a small scale effect. So it's going to be linear in h, linear in g. And so my estimate is, I should go as g. H is also dimensionless. GH over c squared. Check meter squared over second squared. It's good. Now I could plug in numbers. That's what I want you to learn not to do. You don't plug in numbers here inside. You recognize quantities that you already know. You recognize the quantity, a length related to acceleration. That is, if you have g, meters per second squared, you divide it by c squared. That's 1 over a length. Okay? This is a number to know. You put it in your toolbox and then you have it. This number is about 1 light year. If you didn't know, it's easy to remember. It's easy to remember also what is 1 light year. It's 10 to the 16 meters. That's separate part, toolbox that I already prepared. So I put it in here. I'm saying this is h over L acceleration. 1 meter, 10 to the 16 meters. 10 to the minus 16. That's my estimate. I still have 30 seconds. Okay? But now we have lots of time for discussing. We have 10 minutes. You should ask. You know, how did you know this? How did you know that? How do you know that it has to be like that? But you're getting what is that I want. No, so next time is gonna be gravitational redshift. You have a laser, you put it at the you have a laser, you know the wavelength, you ask what's the wavelength that is received, is it larger, is it smaller, by how much? Okay? And let's do that's 10 minutes, and we do that. We don't have to do full 10 minutes, but I want questions now.
How do you know it's equal to g of h?
Good. That's the first question to ask. No? Because if I had computed it, I could say I derived it. And then something one has to know. Like how to start with this. But and you can argue that, in fact, I used it because I used a sense of what the theory tells me. The words that I said are, there's one scale h, there's another scale that I know, 10 to the 16 meters. 1 meter is much smaller. So anything that is proportional to h over L squared is going to be a much smaller correction. So for instance, here you see I could have tau 2 instead of tau 1, but that would be an higher order correction. So if you think of it as a Taylor series, this is the leading order of a Taylor series. There cannot be any order 0, because if they follow exactly the same order line, then it would be not delay. First order in h, so it's first order in acceleration, first order in in height. This one I couldn't guess if I didn't use dimensional analysis. Okay? So I used an argument for one and an argument for the other. There is no claim that this is a proof. An order of magnitude estimate is not meant to be, I prove something. It's meant to be, I've already done this calculation lots of times. I know how to do the full theory, but now I need quickly to know how big is the effect. You could remember this number, and I want next time to know this number. You to know this number. But we are going to keep building exactly in this style. Okay? More questions? Yes.
Could you clarify why, if you used tau2 in the denominator, it would be a higher order correction?
Yeah. So, what's the difference between the two? It's of disorder. So, if I put here instead tau2, I can substitute the other, and then I can expand again. No? And so it's this style of you make the approximations at the beginning and not at the end. In a problem where you want to control precision, you do the opposite. You do approximations as late as possible. In a problem when you want to estimate orders of magnitude, you do approximations as early as possible. So it's really two different skills. Okay? More questions? Yes.
I still didn't really understand why you just do tau2 and try to construct a time by instead you did a divide by 2. I still didn't understand.
Yeah. So I could have asked, what's the difference without dividing? But this time tau1, it's 1 second.
I see.
Why? Because it's about 1 meter. Gravitational acceleration is 10 meters per second squared. That exercise, 1 second, I've already done it in undergrad mechanics. Okay? And so I'm taking away the part that I'm supposed to know already. Because otherwise I would have said it's 1 second plus 10 to the minus 16 seconds. Okay? So I'm identifying what is the relevant quantity. Yes.
I think I forgot what tau1 and tau2 are.
Yes. So good. Yeah. So yeah. Times between two events. So there's the event where this leaves my hand, let's say. Then there's the event where I catch it.
Oh,
Okay. And tau1 is the time along the word line of the wristwatch. Tau2 is the time along the word line
okay.
of the phone that is.
Tau2 is the phone. Okay.
Yes. Thanks. Okay. Okay. One more question.
Where did we introduce general relativity to this?
Where did we use it? Like you see, I didn't do any calculation that requires tensors, but there is general relativity. You could say there is special relativity and not general relativity. Those are names. There's acceleration, and I have to know how to do things when there's acceleration. So it's a flat space. You didn't have to use curvature. So can argue it's a gravitational effect. Do you have a follow-up? Can you say more? Like, what did I use? Like, one can argue, I didn't use much. That's why this is powerful. Sometimes you can use it for things that you don't know yet. And you should use it before, when you don't know something, you haven't learned something yet. You make an estimate before learning it, and then you check later that's meaningful or not.
Is it the use of C?
Yeah, so it's not a Newtonian phenomenon because there's a C. We're going to see effects where curvature is important, where geodesic deviation is important. Yeah, curvature is not important, but acceleration is important. There's a question should come up that has not come up yet. You see, I put a modulus because I didn't want to track signs, but now we can do it as next step. Which one is longer? This one or this one? Okay, I want hands. Think about it first. This one or this one? Which one is longer? This one? This one? Okay, I want an argument now.
Who is observing?
Huh?
Who is observing?
It's two detectors. This is a detector, this is a detector. They both give me numbers. And the question is, the two numbers that they give me, they're both measurements. They are measurements of two different quantities. There is no notion of time between A and B. There's time associated to a trajectory. So there's the time of this trajectory, the time of the time of this watch, and the time of this other watch. So which one is longer? I want an argument.
Maybe the one that's being thrown in the air.
Arguments?
The time dilation due to the gravitational time dilation on that one.
Okay, so this is the second spot where, we want to bring in everything. We did the estimate, but we want also to speak relativistically. So we don't want to bring an external time. Okay, so do that now. Let's look for an argument. So I saw many hands saying this one is the longest one. I want argument for why this one is the longest
Well, the hands one is the longest one.
one. Okay, argument for that then.
So they have the same space-time interval, but in the hands frame, there's a difference in space. And because there's a negative sign between the x squared and the ct squared, so the hands one would be longer.
Okay. It's good. It's good that this thing, if I keep speaking, these things never come up. I would argue that both arguments are not general relativistic arguments. They are the kind of arguments when one learns special relativity using coordinates, Lorentz transformations. So you have taken GR1. Use it. Can you use it? Which one is longer, the geodesic or the one that is not geodesic?
Geodesic.
Argument for that?
Geodesic will be the light travel, which is only the CT, so that's the temporal part. While the non-geodesic will also have the spatial parts.
That's an argument about how you do a calculation. I want an argument about the physics. So when we say geodesic, is geodesic the shortest curve or the longest curve? I see a hand of it. Go ahead, tell you.
Oh, I was, sorry. Because if it's the shortest curve in terms of the distance, but if we're looking for the proper time along the curve, it would be the longest, right?
Good. So let me make sure that everybody's agrees. When you do geodesics in Riemannian geometry, geodesics of spatial course, the geodesic is the shortest curve. When you do timeline, when you do word lines, geodesic is the longest. How can I be sure that I don't forget this and I have to think twice every time? Well, time, space, pick 2 points. This is a geodesic. I could do this curve that is not a geodesic. Is it longer or shorter? Well, I could do this. You go like, you reflect on a mirror, like, you reflect on a mirror, like, you reflect on a mirror. Every time you go like, takes 0 time. So the like part takes 0 time. Everything else is going to take longer than 0. Okay? That's the easiest way to never get confused. A time like geodesic is the longest. Okay? Okay. That doesn't mean that we know which one is the geodesic. Which one is the geodesic? This one is the geodesic or this one?
So let's be thrown.
I want an argument for that.
Because that one is, there's no, There's no other force. It's the one that's being held in your hands. That's an extra force on. It's in free fall.
Okay, force is still a notion that sounds Newtonian. Can you use the definition of geodesic that you learned in GR1? What's a geodesic? I don't want the equation. I trust that you know the equation. I want the meaning of it. Geodesic is a free fall. Geodesic is a curve of zero acceleration. So now I should ask you, which one has zero acceleration? This one or this one? This one is accelerated because the ground is pushing me and I'm pushing it. This one is the one that is not accelerated. In fact, you can use an accelerometer. In your phone, you have an accelerometer. You start the accelerometer and you check, and it measures that when I hold it, the acceleration is 9.8 meters per second squared. Okay? So you see how many things there are inside here? This one, I declared, the drawing doesn't tell you anything, no? Because the drawing is in some coordinates. In fact, I didn't have two coordinates. But this one is the geodesic, is the longest. By how much? By 10 to the minus 16 seconds. And then we can go on and ask, can this be measured? Has this been measured? Where is that number important? This 10 to the minus 16 is going to appear quite a few times. And when you see it, you should recognize it. Okay? So, as you can see, there's a lot of pieces to bring together. No, there's lots of theory, lots of tricks, tool bag of tricks, but also, I would say this is understanding. No? This is understanding. This brings together both the intuition, the theory, the formal part, the speaking general relativity in relativistic terms, not saying if I choose these coordinates, if I check this component, it's a physical phenomenon. It shouldn't depend on how you do the calculation. Okay, you do the calculation in that way because then you want to set up something you can do numerically. Okay, so next time we do gravitational redshift. I would like somebody who does it. It's more fun, but that we can plan. Okay. Is there another comment before we go ahead? Was there another question on the story? There's a question that didn't come up. I think this is good to do. Yes, go ahead.
Can you explain one more time why the tau one is the geodesic?
Yes. So I'm arguing that this one is the geodesic. Okay. So you use the word force. The geodesic is the one, it's the curve of free motion where there's no force applied to it. Okay. So this one, there's a force applied to it. It's my arm, and my arm is going at 9.8 meters per second squared because the ground is pushing. Okay. While this one, there is no force applied to it, and so it's following a geodesic that is this parabola.
So the phone is the one that's being thrown, or the one?
The phone is the one that I'm throwing. This one is attached to my arm.
Oh,
No.
okay.
This one
Okay.
is the one that is geodesic.
Okay, okay.
If you really want to convince yourself, download the app that can tell you, that checks your accelerometer. You all have accelerometers, gyroscopes, things to measure magnetic fields. You have to know all those numbers all the time. If you know, otherwise you cannot estimate order of magnitude. What's the magnetic field in this room? You have to know the number. Otherwise you cannot use it. There are some elementary pieces that you need. And so check with that accelerometer and if you Is it working? Doesn't look like it's working. Okay, it's not working. Yeah. For some reason it's not working. And yeah, if you check, the accelerometer measures exactly that. It measures what's the force applied to it. So that we can discuss another time. There's another thing I wanted to bring up, that is, this calculation is immediate. No, it's 3 10 to the 8 squared, so it's 16, 17, and there's a 10, 16, 10 to the 16. This one is also immediate, right here, no? Because you have the numbers. 1 year, it's 3 10 to the 7 seconds. C is 3 10 to the 8. Right there, you get 10 to the 16. This is a number to know. What's the year in seconds? Make a table, start collecting them. At some point, you have enough numbers that you don't have to go check the table. Yes.
So can you explain the logic again for why the time lag is why the geodesic will be with the
Yes. Yes. So I'm giving you a way to make sure that you remember it. It is just check one case where it's completely clear. The one case where it's completely clear is you have this word line that is geodesic, and you have other word lines around it that are not geodesic, perturbing around the geodesic. Now I'm asking, which one is longer, the geodesic one or the perturbation? Well, I could perturb around it in such a way that the perturbation is always null. Null in the sense of light. Okay? How long does it take to light to go from the sun to here? 0 seconds. How long does it take to light to go from the sun to the earth, get reflected and come back? Twice times 8 minutes. Don't get confused. This is general relativity. Those are two different questions. They are two different clocks. If you have a muon in the high atmosphere and it reaches the ground, it reaches the ground in less than its lifetime, that is 10 to the minus 6 seconds. Okay? So this one is not 0 seconds. This one should be larger than 0 seconds. That gives you an immediate sense of which one is larger, the geodesic is. Then you can prove it, as a theorem. You use very similar technique. That is the intuition. You check that the perturbation shortens them. Good. Yes.
So the reading on the phone will be longer.
Yes. And they're both correct.
Yeah.
No, because time is not a function of endpoints. Time is a function of the path. Like distance, go from here to Philadelphia, it depends what path you take. No, it's not a function of the endpoints, it's a function of the path. Okay. Let's shift gears now. Let's do some theory. Okay. I want to tell you about Hamiltonian formulation. And to do Hamiltonian formulation, we need to know what are the position and momentum for gravity. And you've learned differential geometry for Lorentzian metrics. We are going to have to do one step back, learn differential geometry for things in space and how they change in time. So the plan that I have is to tell you first about surfaces in 3 dimensions and introduce all the notions just for geometry in space, okay? And then use those methods later, okay? So I'm really gonna do geometry of surfaces. I have a surface and I ask, what's the curvature, okay? And you can do these things with elementary mathematics, but you have already learned differential geometry. Let's use it, okay? Where do you learn these things? Well, there's an appendix of Carroll's book, if you like Carroll's book. It's elementary to the point. There's a full chapter in Ward's book, more mathematical, more abstract, where you get all of the ideas. When you do calculations, it's useful to have many techniques. There's a chapter in Poisson's book. Gorbulon has a review on numerical relativity that does all of these things, and it's a good introduction. You have these slides, right? Okay. So the goal is to reformulate general relativity in this language of dynamical degrees of freedom. That is, instead of looking at space-time all at once, you go back and you do physics as you have learned it for everything else. You set initial conditions, and then you ask how things evolve in time. No? You set initial conditions, that is, you say what is geometry at one given time, and then you ask, if I know the geometry at this time, if I know Q and P, position and velocity, what's going to happen later? You see, this makes sense if you are not just guessing solutions or writing analytical solutions, but if you want to do numerical relativity where you set initial conditions and then you actually ask what's going to happen. It makes sense if you want to do quantum gravity, because when you do quantum mechanics, the most immediate thing to do is you identify Q and P, you quantize them, and then you ask what's the dynamics. So it's this logic of separating kinematics from dynamics, easy from art. Okay, so that's the goal. Let me do some easy mathematics, and then we go back. So let me start with this room, 3D Euclidean space. So I fixed the structure. It's a manifold, it's R3, and there's a metric that is the flat Euclidean metric, and I can use Cartesian coordinates. Now I want a surface, okay? How do I describe the shape of a surface? Well, I say it's a two-dimensional manifold. I can put coordinates over it, I can draw a grid, and I can think of it in two equivalent ways. They're both gonna be useful. One way is to think of it as a constraint. This one is the surface where a certain function of x, y, z is a constant. Okay? There's another way that is the embedding. The embedding is for any point on this surface, this is also a point in 3D space. And so for any two-dimensional point, I associate with a three-dimensional point. Okay? Now, there's something to bringing back when you learn general relativity the first time you have to extract, because when you learn about curvature in general relativity, it's four-dimensional curvature, intrinsic curvature, not curvature something into something else. But here you have two notions of curvature. You have the intrinsic one of the two-dimensional thing. You have the extrinsic one of how this one is curved in the ambient geometry. Okay? And so these are two notions. The intrinsic one is a metric, is a Riemannian metric. And the extrinsic one, we're going to learn that it's a symmetric tensor with some properties. Okay? So to be as concrete as possible, I'm going to take an example. I take this surface, a cylinder, and you can write what's the surface. So let's see, x, y, and z. It's as constraint is this constraint. As embedding, you can think of the top part as being z equal this function. That's an embedding. Is x goes into x, y goes into y, and z goes into this. Plus or minus, so that you get both parts. Okay? This gives you an immediate way of determining the metric, because you know the metric of space, then you have dz, you can plug it in here, and you get the intrinsic metric. Okay? Simple calculation. So now you know what's the intrinsic metric. And once you know the metric, you can ask what's the curvature. You just use the machinery that you have. Okay? And as usual, there are always these three layers. Do you know the theory of how to define that curvature? Do you have an algorithm for computing it if you want all the details? And do you have a quick way of estimating how big it is without doing any calculation? I want you to be able to do all three things. No, the theory, the exercise, and the problem. All this was intrinsic geometry. But then there's a separate thing that is extrinsic curvature. Extrinsic curvature is not about internal properties, but about how the normal changes when you move the normal around the surface. So for instance, if I put it this way, I would say the extrinsic curvature is 0 because I move a point and the normal doesn't change. If I put it this way, there should be some extrinsic curvature. So let's do a check of what I said makes sense. So intrinsic geometry of a cylinder. Riemann tensor. What's the sign? What's the value? Is it positive, 0, negative, undefined? Think about it for a moment, and we vote first, and then we discuss. You're allowed to complain. The question doesn't make sense. You didn't tell us enough, but I want you to vote first. So said cylinder, I said intrinsic, and I'm asking about Riemann. Positive. 0. Negative. The question didn't really make sense. Okay, so I want to, and don't hesitate, raise your hands. Make a choice so that then you can be surprised. Or if it was right, then you will get more confidence for the next time to be surprised. So I want an argument, like undefined, complaint. Tell me all the complaints. Yes.
Right now, I'm not sure how to go about this. I have a very definite shape.
So what's the undefined? Is it because it's a tensor, or is it because I don't know how to compute it?
Because it's a tensor, and I'm just not connecting it how we are gonna look at a cylinder.
Yeah. Okay. So let me go one step back. So this is the metric of the cylinder with the writing. So as a calculational question is, take this metric, plug it into your machinery, and compute the curvature tensor. And sometimes I do it by hand. Sometimes it's useful to just have a code that does it for you. I'm going to share my mathematical one that is unmade. I just use it all the time. I know it's stable. Write your own. Use something that is, I don't know, already written. Have your way of computing curvature quickly when you need it. Sometimes you just need it. You want to know the answer. Okay? Have always a way to compute curvature components. Sometimes you have tricks to say what's the answer without computing. Those are not enough. Okay. Then there's certainly the complaint that is, oh, you're asking me the sign of a tensor. Hey, I know sign of numbers. What's a tensor? So maybe that you could contract things and say Ricci scalar. Let's forget about the tensor. Let's say Ricci scalar. I was allowed to say tensor because in 2 dimensions, Ricci scalar is all there is. No? But in 4 dimensions, I have to say which components. Okay, so let's say Ricci scalar. So now it's a number. The sign doesn't have to be the same everywhere, but there's a lot of symmetry. So maybe the sign is the same everywhere. So do you want to change your answer now that we have thrown away this one? Is it positive? The curvature? Is it 0? I want an argument for 0. Like positive or negative, you could still complain like, what's your convention for the sign of curvature? Does a sphere have positive curvature or negative curvature? I say positive, but you can still complain that that's a convention. You would have to decide. 0, I want an argument. 1 and 2.
Oh, I mean, we're talking about intrinsic curvature, forming the cylinder, your example, like taking this flat piece of paper, curling it up. So theory that embedding of the flat piece of paper, the intrinsic properties of that curvature shouldn't change. That is
Good. Let me repeat the argument. You're saying, I know that this piece of paper has 0 intrinsic curvature. It's flat. Now, when I do this, I'm not deforming the intrinsic geometry because this is rigid enough. It's not extrinsically rigid, it's intrinsically rigid. And so the intrinsic curvature shouldn't change. The extrinsic, yes, but intrinsic. And so 0. You have a flop.
I was gonna say that, if you try and parallel transport a vector, and if you move it up and down, it's not gonna change, and then if you move it around, it's not gonna change. Then, no matter how you parallel transport.
Good. Okay, so this is, let's not use the trick that I know that this is 0, and so that means 0. Let's use our intuition. We want to make sure that you have an intuition for what's the Riemann tensor. Riemann tensor is, as you're saying, you have a vector, you transport it around a loop. A loop is a plane, so it has 2 directions. The vector goes into a vector. So these 2 indices tell you what's the plane. And this one is the matrix that sends a vector into another vector. Okay? What's the Riemann tensor? Riemann tensor is a thing that is, take a point, take a loop, take a vector, transport it around. When you come back, that vector in general is going to be rotated. By how much? If it's rotated, then there's curvature. If it's rotated in the same direction of the loop, it's positive curvature, opposite direction, negative curvature. Which components of the Riemann tensor? Well, these ones are the ones that tell you the plane, and this one is the rotation matrix. Okay? And so now let's go back. Here, if you take a vector, you take a loop, you can check that if you do the parallel transport for an infinitesimal loop, but even for a finite loop, the vector doesn't change direction. If you go up, doesn't change. If you turn around, doesn't change. And so it doesn't change. Yes.
Could you say very quick again what you mean by the plane?
Yes. So in 2 dimensions, there's not enough space to have. These 2 indices can only be 1, 2. It's antisymmetric, so it can only be planes. But in 3 dimensions or in 4 dimensions, you would say, let's say that we have 3 dimensions, and you do this loop, this one, x, y, the plane that the loop lies in. Okay, and then if you go from here to here, you still have a vector that you have to transport around. And so if you want, you have a vector v mu that is going to be sent into the vector v mu plus at first order the correction that is v nu times a matrix. What is this matrix mu nu? Is R mu nu rho sigma dx rho wedge dx sigma, where this is the plane xy. Okay? Good. Let's do extrinsic now. Extrinsic curvature. K mu nu. Is it positive? Is it negative? Is it 0? Positive? The sum of the 3 has to be everybody. Let's participate. Is it positive? I see 2. Is it 0? Cylinder, is it 0? Yes, that's equal. I see nobody. Is it negative? Should I assume that everybody else is complaining? What's the complaint? So again, K mu nu, it's 2 by 2, it's symmetric. So it's fair to say you still have to tell me which components or which properties. So the ones who said positive, what did you mean when you said positive? Can you say explicitly?
I was thinking about when you said that if the vector changes like along the loop,
Yeah.
the same direction as the loop, then but I'm It's not completely clear in my head, but it seems kind of like it would be in the same direction.
Okay, let's be careful though. I'm asking about extrinsic curvature. The statement before was about intrinsic. The Riemann tensor tells you when you transport a vector that is in the plane. Now I'm asking about extrinsic.
So then as well.
So this is about the normal. So the question is, if I take the normal, and now I move the normal, and move the base point, is the normal changing or not? I want to say, yes, look. And is it changing so that it converges or it diverges? So then there's a matter of saying, are you speaking about the normal going out or the normal going in? The one going out. No, I didn't say it, but extrinsic, extrinsic is going to be like velocity. Velocity towards the future or towards the past? Towards the future. Okay? That's what extrinsic curvature is going to be our velocity. Okay? Extrinsic curvature in time. Here, going out. And so when I move, it diverges. It points doesn't converge, it diverges. And so you would say positive. Oh, but wait, what if I move up and down? It doesn't change. So this one is also okay as an answer. But why there are two answers? Well, this is a tensor. It's 2 by 2. It's symmetric. It has two eigenvalues. 1, 0, 1 positive. Okay? So you should have complained. This one was one to complain about. Can we do the calculation? Yes.
Why? How do we know that the normal is gonna be outward?
Yeah, we have to. It's part of the definition. We have to declare it. No, you have to say extrinsic curvature of the oriented surface.
Of what?
Extrinsic curvature of a surface with given orientation.
Oh, okay.
No,
So
it depends on
could
the.
be negative.
Could be negative if I took the other orientation. It's like velocity. You have a world line and you ask what's the velocity? Is it going to the right or to the left? Well, it depends if you reverse time and say we're going to the right and go to the left. And so for time, you can use the direction from thermodynamics, the one where the entropy increases. For surface, I don't know, if it's a ball, you say the exterior. Yes.
We're saying like distinction between positive extremes and negative extremes. It's about like what are the vectors converge or diverge in what sense of like when you say converge in some direction, what
Yeah. So let's put in some mathematics so that we have the structure of mechanism that should address your question. So you see, this is the picture for intrinsic curvature. You take a loop, intrinsic curvature or Riemann tensor is not the definition with the contraction. You have to think about the geometry. The geometry is take something finite, transport a vector, transport a gyroscope along a closed path, and ask if the gyroscope is rotated or not when you go back. Now, that's going to depend on this full path. But now I'm going to shrink the path and make it infinitesimally small so that it's really a property of not the point, but the small neighborhood, the first two derivatives at that point. Okay? That's the meaning of the Riemann tensor. And so, for instance, on the cylinder or on the plane, you see that you take a vector, you transport it around, you go back, nothing changed. I'm going to skip this. Now, how do we do extrinsic? Let me see if I have directly the answer. Let me give you the answer. I don't want to, we don't have to go through all the mathematics now. There's all the details there, but you can introduce a notion of normal, and I'm separating the way of how do you find a formula for the normal. Once you have the surface, you can define the normal to the surface. Okay? So how do I tell if this thing diverges or not? I have to know how to move it around and ask if it diverges or not. Well, covariant derivative helps you. Okay? So you check this covariant derivative. And I should have an example. I think what's the best way of doing it? Yeah. So this we will take time to do. And this is important because it's going to be these two exercises where you learn how to compute extrinsic curvature. We're going to go through the theory. You are going to derive all the theory for building the pieces to compute extrinsic curvature, and then use it. And use it for computing the intrinsic and extrinsic curvature of the sphere, the cylinder, and of a saddle. Okay? And maybe there is one thing that I should say to close this lecture. That is, there's something that is going to be very useful to prove and put it in our bag of tools from differential geometry. That is, you have the curvature in this row. It's 0 for all approximations that we need. And then there's this surface. It has an intrinsic geometry and an extrinsic geometry, but they are not independent because this surface lives in that external space. There are going to be relations or constraints. These are called the Gauss-Codazzi relations, and they're going to be the constraints of general relativity. And they are the form, the curvature in this room, the three-dimensional Riemann tensor, the curvature of the surface, and the extrinsic curvature of the surface. They are not independent. They are related by an equation. Okay? Now, in this room, the curvature is 0, which means that these two objects are related. For a cylinder, we also found that this curvature is 0. So yeah, this is 0, this is 0. That means that this combination of extrinsic curvatures has to be 0. You recall before I told you there are two eigenvalues, one positive and one 0. This is going to be related to the determinant. It's product of the eigenvalues. That's why it's 0. In particular, when you work it out for a two-dimensional surface, you find that the curvature of the surface is equal to 2 times the product of the two eigenvalues of the extrinsic curvature. And this thing has a name, theorem egregium. But more than a name, it has a very clear interpretation. It's a notion of rigidity. The notion of rigidity is, suppose that I hold this thing this way. Okay? By doing this, I'm making sure that one of the extrinsic curvature is non-zero. Okay? Now this surface, I cannot deform it anymore. If it's both are 0, I can deform it as I want. If I set one be non-zero, the other necessarily has to be 0 because the product has to be 0. Okay? Sometimes people, instead of attributing it to Gauss, they call it the pizza theorem. Clearly, that's what makes it rigid. Okay? Going back and deriving this property from the full theory, this is a good exercise. This is going to be one of the exercises. It is going to be B4. Prove it. Yes.
I want to tell that Frederick might be still.
Say it again.
I think I'm still building this, but if you will, I think it's still like. Like.
Yeah, so I'm saying once I put 1 on 0, then the other necessarily has to be 0. That fixes the embedding in the sense that if I want to deform this, I really have to tear it apart.
Oh.
No? And so if you fix the intrinsic geometry, it is this has 0 intrinsic curvature. And then you ask, what are the embeddings of something with 0 intrinsic curvature in 3 dimensions, where also it's 0 3-dimensional curvature, the embedding is rigid.
Oh, okay, so you want that.
Okay. Good. We still have 5 minutes. What did I skip? I skipped pieces that are useful for doing these 5 exercises. Okay? What do we do next time? We go slowly through them. We build all the tools. We have to do it exactly as when we learned differential geometry, exactly as when you learned calculus. We have to build the pieces for doing Hamiltonian formulation generally. So there's a part of it that is the familiar differential geometry, but for Riemannian quantities. And there's a part that is new, that is all this extrinsic part. We're not going to do it for surfaces. We're going to do it for 3-dimensional space in space-time. Most introductions, they just do directly that. You want to understand this, do it first for a sphere, for a saddle, for a piece of paper. Do as many of these exercises that build intuition as you can. Okay? So that then when I ask you what's the order of magnitude of the curvature of, you don't have to do again a calculation. You know already what it depends on. You estimate only what you need. What is the curvature radius? So that when I ask you, what's the curvature scale in this room? Is it larger or smaller than this number? You know immediately. Okay? We're going to use that then for black holes, for cosmology, but if we don't know them in this room, we don't have a sense of what are those numbers. Okay, so that's the plan for this term. We have 5 minutes. Ask questions about anything you want. We do have.
Can you explain again what are K1 and K2?
Yes. So extrinsic curvature is a tensor. 2 indices symmetric. Okay, so you can look at the eigenvalues. K1 and K2 are the eigenvalues. We're gonna do that. No, what I wanted to make sure today is that we have a picture of what are the questions and what we should expect for something simple like a surface. Next time we're gonna go slowly and build the mathematics. Then we go back. We ask again these simple questions first. And then we do it for black holes, for neutron stars, for cosmology. Okay? So as you see, the homework has 5 exercises that are just a piece of paper, deform it, compute. And then the next 3 are do neutron star, do black holes, do cosmology. Right? Yes.
So the extrinsic curvature tensor is 2 by 2 only for 2-dimensional surface?
Yes.
In 3D. Or is
That's a good question. So it's a surface tensor. It's as many as the surface for which you're computing the extrinsic. So if I did a 2-dimensional surface in a 26-dimensional space, it would be still a 2 by 2 tensor. And the reason is that naively one could say, well, but the normal can point in any direction. But the change in the normal can change only in the direction of the surface. Okay? And so you can write it as K mu nu, but it's really a KAB. So that's another tool that we need. We are going to know how to be quick and play with pullbacks without having to write long formula. You're gonna need the pullback of a space-time tensor into a space tensor. More comments or questions? Yes,
A follow-up, so then for a three-dimensional surface, space-time, it would be 3 by 3.
that's good. That's good.
So if you want to describe the geometry of the space, do you need both the unit tensor and the extrinsic tensor?
Good question. So we have two languages that are equivalent. You can call one Lagrangian and one Hamiltonian, one trajectory and one position and velocity, one space-time and one space and time. Now, you can work with Jimmy and you and Riemann tensor of space-time, or in a completely equivalent way, you can say, I just tell you about space, the curvature of space, how the curvature of space changes in time, and how the extrinsic curvature of space changes. The two things are equivalent, can go one way and come back. So why have two languages? Why do we continuously have to go, like you can work in one language, you can work in the other, but it's good to know both and translate between one and the other. The reason is that there are advantages in one and in the other. When you work with space-time, with Jimmy and you, there are space-time symmetries that are manifest. You know, no, things are covariant. But if one asks, okay, I know what happens now, can you tell me what happens tomorrow? Well, that formulation already assumes that you know what happens tomorrow. No, you just find just the solution, not the initial conditions. So these are questions of, important if you want to solve a problem numerically, say, what are initial conditions? Important if you want to look at the space of solutions, and what's the full space of solutions of general relativity? It's not the solutions that we find because we know them exactly. If you want to know all of them, that's too difficult, but you can still say, well, I tell you the set of independent initial conditions. I haven't solved the equations, just telling you what I can predict. And that's a powerful tool. It's tool developed in the 60s, that is way later than all the rest, but it had an incredible impact on the development of general relativity. So you can think of this full part, this full part one is about that. It's about Hamiltonians. No? I didn't say one more reason why this is important. If you want to ask what's gravitational energy, what's energy, you want the Hamiltonian. This is made for doing that. Okay?
So would be knowing both the intrinsic and the extrinsic curvature the same as knowing the GPV?
Yes, it's correct. But there's a part that is highly non-trivial. It's like saying, if I know the position, the initial position, initial velocity of a particle, I also know the full trajectory. Once I solve the equations of motion, okay? And often solving the equations of motion is the difficult part, but you can identify a solution by saying what's the initial condition. Good, that's all for today. Thank you.